Okay. All right, there we go. All right, so I'll get, well, actually, let's do the opener first. What is the major difference between fission and fusion if they both involve creating energy from the nuclei of atoms? Okay, so they're both nuclear energy. Okay, they both give off energy. They both do. But what's the big difference between fission breaks things? So what does fusion do? Puts them together. That's exactly correct. Okay, so if fusion fuses two different nuclei into one, that's what our sun does. That wonderful hydrogen bomb in the sky that's being hidden by clouds right now. Fission, on the other hand, is the one that we've learned how to harness here on the planet. We've really learned how to do both, but it's semantics right now. But fission is what we do in nuclear reactors, where a larger nuclei, such as uranium-238 or thorium or plutonium or any of the other ones that we use in weapons, where fusion brings things together, fission is going to split things apart. It's a fissure or a crack. It is a breaking down. That's the two. Looks like I've got somebody else online. Who's online? St. Reagan Lucas. What? Your mom yelled at you? Just shave your head. Do it. I keep thinking that I'm gonna like shave my head, but I don't think I'd look good bald because my hair drives me nuts. Alrighty, let me pull the right stuff up here. All right, so once again, Unit 12 review is right here. The test is below. Yes, you can always use your review on the test. Okay, so the big difference between fission and fusion is fission is a fissure or a crack. So you have a bigger thing that's breaking into smaller bits. Whereas fusion, like our sun and like a tokamak generator, which we haven't quite figured out perfectly yet, there's going to take two smaller atoms and going to fuse them into a bigger thing. Y'all probably are not like with the Dragon Ball Z era. Well, you might be. Where they like the golden haired dude, like when they fuse. Okay, so that's fusion. They bigger, better. Lots of energy. I don't know what I did with that. I accidentally showed my Earth Space kids the gallery of earthly delights. There were naked people on my screen. Where's my remote? It's a painting. Not normal. Where is my? Is it not right there? No, not where? No. The little skinny one. We're doing documentaries and 3 days of global warming documentaries by Leonardo DiCaprio. Fun. Go in the hole. There we go. All right. I'm not going to go over the vocab like on here. Okay, but this vocabulary is on the test where I just did fission and fusion. Fission is a split. It's a bigger element breaking down to smaller bits. Fusion is a couple of smaller elements. In the case of our sun, hydrogen, fusing with hydrogen to make helium. Isotopes, same element, different numbers of neutrons. Critical mass would be, it's the amount of a radioactive substance that is necessary to allow the sequence of events. Like you have to have a certain amount to make it go. That's critical mass. Chain reaction would be said thing. Acute is like a one shot in the dark. Chronic is repetitious. Background radiation, we're being exposed to it right now. It's everywhere. It's from the sun. Half-life. Now that was one of the things that we did yesterday in the slides, where it like I think the first one was like it was a 3-hour half-life. So when you have one half-life, you cut the starting amount by 2, and then that amount after the next half-life, you cut that by 2. There is a formula for it, but I didn't even show you guys. I showed 8th period and they like freaked out. I was like, don't worry. It's just, you just cut it in half, however many half-lives you have. The top one is the base equation for fission. You have what kickstarts the reaction, in this case is a neutron, okay? This is uranium-235. There's 2 different types of uranium, 235 and 238. So the neutron is like catalyst, and it's going to slam into the uranium, and it's going to make it break down into smaller bits because there's too much crap in the nucleus. It's like too much water in a water balloon that pops, like sort of. So when the uranium pops, it's going to make krypton 92 and barium 141, and it's going to give off 3 separate neutrons, which are then going to go off and slam into other uraniums. This is what happens inside a nuclear reactor. And yes, it gives off energy. Causes heat, heats up the water, makes steam, spins the turbine, and voila, we turn lights on and off. Fusion, on the other hand, in this case, we've got tritium, tri meaning 3, and deuterium, du meaning 2, that are combining together to make helium, and it does produce a neutron, and it gives massive amounts of energy. Now, if you did not notice when we were doing the fusion and fission, like the math, your masses had better add up. Okay, so 3 plus 2 is 5. 4 plus 1 more is 5. Like they should add up to the same number. You're not God. You cannot create or destroy matter. In fact, the different elements are made by our stars. And if you take me for Earth space next year, you'll learn that the carbon in this hand, even the different carbon molecules in this hand can come from 2 totally different stars because we're literally made of stardust. And I'm not joking. That's where the heavier elements are made, is in the stars. So they both make energy. Fusion makes way more energy than fission. Our current nuclear power plants use fission, and we do have fusion tokamaks. They're not productive yet. But we're working on it. We've been working on it since the 60s. Symbols. You need to know all of this stuff. An alpha is a helium nucleus. You've got a total mass of 4. Okay, you've got 2 protons and 2 neutrons. 2 plus 2 is 4. When you do have alpha decay, you're reducing your protons by 2, and then you have to look up that element and change it. So we've got a mass of 4 atomic units, 2 of which are protons, 2 of which are neutrons. The total net charge of an alpha particle or alpha decay, same thing, is going to have a charge of +2, because you've got +2 in neutral. There's no electrons. It's not a helium atom, it's a helium nucleus. So you're going to have a reduction of 2 for the atomic number. You look that up, and that's the element. This is the largest of the particles, so it can't penetrate into small spaces as easily, so it's the least dangerous. You can still die from this. You can still get radioactive poisoning. They're all dangerous. It's just the least dangerous of the 3 because it's the largest mass. The smaller the mass, the more dangerous it is, and this was part of the slides that you guys did yesterday. If you literally put a sheet of paper in front of you, if I was shooting alpha particles at you, they wouldn't get to you. Not that I would do that, because we don't have alpha particle guns. Huh?
What's the particle?
The particle?
Particle is different than
It says, hold on here. Symbol here. Particle is, okay, charge. Oh, yeah, I just so totally yanked this out of something else. All right, so the charge is +2. Penetrating ability is low. You can stop it with paper. This is the symbol and technically the particle as well. But an alpha does have a +2 charge. But what? Who? It's basically the same twice. A beta is going to be the next dangerous. Okay, so this is how we represent it. It has no change in mass, but it as far as your, no, that's not true. Well, the top number, the isotope number will not change, but your protons change. It changes the element itself, but the mass does not change. Technically, its mass is that of one of an electron, which is like 0.0054 AMUs. What it does is it's going to, from the parent to the daughter, it's going to increase the atomic number by 1. Okay, so it's a different element, but the mass doesn't change. The top number does not change. This has a medium level of danger. It's more dangerous because it's a heck of a lot smaller, easier to get into the pores of your tissues, into your flesh, and we can stop it with aluminum foil or wood. So really, the symbol and the particle are pretty much the same thing. It's an electron. It changes your proton, but alphas reduce protons by 2 to go from parent to daughter. Betas increase protons by 1 going from parent to daughter. And they're not being sexist. It's just the term that they use. There's no such thing as a son on here. It's just not. Gammas, these are the most dangerous because they have no mass. -1. Alpha's positive too. We just don't put a plus here. But beta is -1. Gamma has 0 anything. It is pure energy. That's what our sun is constantly emitting. You just can't see it today as it's doing its wonderful hydrogen bomb self, giving us life and all that good stuff. It's just a good thing that our magnetosphere deflects the gamma radiation. If we didn't have the magnetosphere, we'd be like Mars. We'd just be dead. So no mass. It is pure energy. Why is my computer wigging out over here? Sorry, y'all. I must have 50 different things going on. Okay, there is no change to the nucleus. There is no change in the mass. There's no change in the atomic number. It is the same element. Okay, my glasses are black. This has the highest of the 3 because it is the smallest of the 3. And the way that you stop this would be lead, about 4 inches thick of lead, and then multiple feet thick of concrete. And when you go get x-rays at the dentist, that's what's inside that heavy vest that they throw on top of you is lead. It's just to protect the vital organs that are in your abdomen. Nuclide symbols, zinc 66. All right. I'm gonna have to make sure you guys have access to periodic tables. I don't know if I'm just gonna have them out or link them into your thing out. I don't know. I haven't figured it out yet. But you're gonna find zinc, which is on here somewhere. There it is. Zinc has an atomic number of 30. Okay. This isotope has a mass of 66. Okay. The hyphen number is the top number. You have to look it up on the periodic table to get the atomic number, which is the bottom number. So zinc is represented with a Zn. And the top number is given to me in the isotope notation of 66. I have to look this up on the periodic table to find out that its atomic number is 30. So zinc has 30 protons in its natural state, also has 30 electrons, although I'm not worried about that here. But when I subtract the two, this particular isotope of zinc has a number of neutrons when you subtract of 36. And when I find it on here, the average atomic mass of zinc is 65.38. So The 65 version of zinc is way more prevalent than the 66 version of zinc. That's why you get these decimals on the periodic table. Give the number of protons and neutrons in samarium 149. I gotta find samarium. Down here on the bottom, okay, it's atomic number 62. And you change the atomic number, you change the element. So it's gonna have 62 protons, period, in the source. When you subtract 62 from 149, the difference, as long as I didn't screw this up, let me make sure I didn't mess this up. Is it 87? Okay. I don't know full well if I make typos, you get the deal. But when you subtract the hyphenated number, which is the total mass, from the atomic number, which can't change, or you change the element, the difference between them is your number of neutrons. This little nuclear unit really does pull a lot of stuff from about the second 6 weeks on together. And I know I did not finish the last slide because I had to go home and take care of my dog that is pooping blood right now. Well, hopefully not this second, because that's disgusting. Oh, poor dog. He thinks he's in trouble. So gross. Now we're going to, you're going to have multiples of these, like multiples of these on the test. So I've got americium. Its atomic number is 95. It's in this particular isotope, its mass is 243. It is undergoing fission. It's breaking down to multiple things. And apparently this is undergoing alpha decay. So what happens with a helium nucleus? Do you add or subtract the bottom number? Okay, so 95 minus 2 is 93. Okay, 243 minus 4 is 239. Now, all you have to do is look up the atomic number of 93, which is neptunium, which I don't memorize that thing. You don't have a whole stack over there. Now, and like I said, a helium nucleus is alpha decay. You have multiples of these on the test. Now, this middle one, are the numbers the same on both sides? The 60, 60, and 27, 27.
Yes, I was looking
So
at
60 minus 60 is 0. 27 minus 27 is 0. Okay, so this is a gamma radiation. This is a specific radioisotope of cobalt. Just sort of blue in color, actually. This particular one I know is beta, where the beta is an electron. So I'm not going to change my mass. Okay, so my top number is going to be 234. 234 minus 0 is 234. 91 minus a negative 1, which is really plus 1, is 92. And then when I look that guy up, this is uranium. You have to have the same amount on both sides. That's all. Like I said, the law of conservation of matter or mass, I've heard it said both ways, just means that however much you start with has to be how much you end up with. They have to equal each other. Are there any questions how I figured out? Because, I mean, you guys have like 5 of these on the test. What radiation dosage is safe for unborn babies? What's the correct answer? What's the best answer to this?
0.
None. That's exactly correct. Because even at 25 millirems, like, you're going to have blood issues. You don't, once again, ladies, when you go to the dentist and you get x-rays, they are supposed to ask you if there's any possibility that you can be pregnant because they won't give you an x-ray. They're not allowed to. Now, I had somebody ask, like, what happens if you break a bone and you're pregnant? I'm not sure. I don't know if they just like wrap you in like 1,000 lead blankets. I don't know.
They can deal with it.
Yeah, they can. I mean, hopefully it's just a simple fracture and not one where the bone's actually sticking out of your flesh. Those are always great. There's really two people. Who discovered the Curies did? They were husband and wife. Marie was actually the one that named it radioactivity. Curium was named after them. Radium was named after them. They both died a horrible death because of their work, but hey, all in the name of science. Fission and fusion observed in real life. Okay, so how do we use these things? Positively. Okay, nuclear energy is one. And I don't even know, that's probably going to be the first. Oh, it is. Nuclear reactors, it is the first one. How else do we use this?
X-rays.
Okay, so the one that I have up here, we don't just use chemo anymore. We have what's called proton therapy, where we actually, what?
What was number 6? I didn't get
I don't even know. I'd have to look. Oh, the Curies did. Marie and Pierre Curie. So we do actually fight cancer with gamma radiation now. It's called proton therapy. It's much more targeted than chemo. And if I did not mention this the other day, if you've never known anybody that's gone through chemo, you're literally poisoning the entire body, hoping to kill the cancer. Okay, proton therapy, on the other hand, is very targeted. And yes, they are using radiation to try to kill wherever said cancerous growth, whatever it is, occurs. All right, so space exploration. The two Voyagers that were launched before I was born in the late 70s, they still have their nuclear fuel. They're still going. They are truly interstellar. The first one punched through in like 2014, and the second one punched interstellar at like 2019-ish. This was part of what you guys read. So the way that we bind things. So like these, now I don't know for sure, but this is a veneer. And you can see with this one, it's got like a plywood kind of underneath, or underneath. I so just meshed two words together. But this top part, this veneer, part of the way that it's bound to the plywood type material that's underneath the desk surface is done through radiation. Spices. So like when you go to cook, although most of you probably don't cook, your parents cook for you, things like thyme, oregano, I don't know, all the different spices that you use to make your food taste better. Those little vials are actually sent through almost exactly like what you see at the airport, like a conveyor belt, and they're irradiated as they go through it. And any kind of bacteria, or you have to understand things like salsa have so many different parts, and even chocolate and so many different like cockroach legs. Oh, I could so really good feel. But they irradiate it. And so even if there was something that was there that could have caused some type of contamination, if you will, as they're pushed through this nuclear conveyor belt, it kills it. Spices, if you never open them, they're going to lose their potency, but they last forever. They really do. And there's tons and tons and tons of other things. There's like nuclear submarines, and warheads, and like all different kinds of crap that I can put up here, but I'm not going to do it. If you ever have something like intestinal major issues, it could be anything from a appendix issue, diverticulitis, Crohn's disease, any kind of intestinal issue, they're going to give you a radioisotope of barium. My mother had to do this. She said it felt like she was drinking gasoline. That was the sensation, not that she's ever drunk gasoline, mind you, but that was the sensation that she dealt with. But what you do is you drink this radioisotope, and then they take an image of you, and it fluoresces the right way. and it helps figure out if you've got a bleed, if you've got a stint, a stricture, a narrowing, that kind of stuff. I've never had to deal with that before personally, but yeah, that was my poor mom. She said it was horrendous. I didn't go too far into this. This is the one that I did not animate. So the last bit says, be familiar with nuclear accidents and the nuclear weapons were used. There were the two bombs that we dropped on Japan in World War II, Hiroshima and Nagasaki. We had, it wasn't just a meltdown, it was an explosion of Chernobyl. Went as far away as Spain. 3 Mile Island was the one in Pennsylvania that happened in like 79-ish. I didn't add more onto this. This is where I ran out of time because I had to go take care of my dog because he's pooping blood. But there's lots of stuff. That nuclear gallery walk that you guys did, that's pretty much what would have filled this thing in full. Now, like I said, you guys do have your test tomorrow over Unit 12. Your notes, if you have not been organizing them, I don't know lots to use. Oh, that's going to bruise. Gosh darn it, that's going to bruise my knee. Oh, yeah, that stings. Let me go in and, how did I just knee my desk? Okay, so for you guys, your notebooks, okay, they're technically due today. Your link, my Earth Space is different. Your link is actually open through 11:59 tomorrow at night. If you do not get this thing submitted by then you're going to have a 0 for a test grade. Eh? Until 11:59 tomorrow evening, yes. Oh, I want to say it's an hour. Yeah. Let me stop my presentations. Stop recording.